All right, no time for introductions. Let's get to work. Okay, so for this um, we are given M1. We're given two blocks attached to a pulley system of some sort. M1 is equal to 35 kilograms, and M2 is equal to 17 kilograms. This ground right here, underneath M1, has a coefficient of kinetic friction that is equal to 0.28. Okay, so go ahead and draw out the forces going on in this free body diagram. Go ahead and make an attempt at doing that. Okay, hopefully you've paused the video and tried to do that. These are the forces that are the most that are present. So one, we got the force of gravity. F for the force of gravity on block 2. We have the force of gravity on block 1. We also have the normal force the ground exerts on block 1. And we also have the force of kinetic friction on block 1. You might be wondering, why didn't I draw any tension forces? And the reason is I usually leave that for last, because if you try to draw, at least for me, if I try to draw tension forces at the beginning, it becomes quite difficult to determine. Actually, you know what? No, it won't. Let me just go ahead and draw it. Let's not make excuses. Force tension on block 1 and force tension on block 2. Okay, so now with that said, it asks us, what is the acceleration? What is the acceleration I believe this entire system experiences? Let me just double check. Of the hanging mass, not the entire system. Okay, so the magnitude of acceleration on the hanging mass. So let's see. Well, it's quite simple. The acceleration for the hanging mass is equal to gravity. See if that is not the acceleration I wanted to see. If I get you, if I got you, don't worry, don't feel bad. We will learn why that is not the case. So for this right here, imagine your, let's say you have two cars, right? You have two cars. This car right here on its own is capable of generating force F, right? That will force is equal to mass times acceleration. So for its given mass, it's able to accelerate this amount. Now what happens when it attaches it to another mass? This second car, we'll call it M2. Well, we're still exerting the same force, but now F is going to be equal to not the net force. It's going to be equal to M1 plus M2 times some acceleration. And if you can imagine this in real life, a car like such as maybe a tow truck can drive pretty fast on its own, but when you have another vehicle attached to it, it starts to drive slower. And the reason is, at least in this, if you think of it as an analogy to this, the truck exerts the same amount of force going forwards, but now it has more to pull. So because it has more to pull, because the mass increased, the acceleration will decrease. So it'll be accelerating slower. And the same is true for this, because this block is being pulled down by the force of gravity. It would fall with the rate of with the acceleration of g, which is equal to 9.8 meters per second squared. But it's not pulling just itself, it's pulling this as well. And not only, yeah, it's pulling this as well. So we have to consider all of this in this case. So the force of gravity, which is going to be, let's draw this in a way that probably will make more sense. So let's draw this in space. Let's say this is space, and there's no gravity, there's no anything. There's just these two blocks, same blocks, except with these, not except, but with the same forces as before. Fg2 Fk_F1. These are the only forces that really matter in this direction. So Fg2 pulls on both of these, and Fk1 is the only opposing force. So the F net, the net force, is going to be equal to Fg2 minus Fk_F1. And if you're wondering how I knew that the force of kinetic friction would be less, well, the truth is, kinetic friction is an opposing force. Friction doesn't exist unless, at least if it's static friction, if it's kinetic friction, it does not exist until the object is moving. So if the objects are moving, then this is overcoming this force, and it's accelerating this entire system. This cannot exist without this one accelerating the entire system, moving the entire system. Kinetic friction does not exist without movement. So Fg2 minus Fk_F1, that's F net. So let's find F net. In this case, F net is going to be equal to mass 2 times gravity minus Fk_F1. Now this is where it gets a little tricky, especially if you have not learned friction yet. I will post a video, not post a video. I will put a video in the description that helped me understand, at least refresh, on the concepts of friction, and I hope it'll help you understand it as well. Go ahead and check the description. Pause the video here, open that in a new tab, and learn that if you don't already know friction yet, and then come back here after that. Okay, so with that said, friction, at least we're given this. Okay, so let's work with this. The coefficient of static friction is going to be the force of kinetic friction over the force normal. Now let's think about this. The force normal is, let's think about this. So actually, no, let's not think about this because you've already watched the video, right? And you understand it pretty well, hopefully. So in this case, we would just need to manipulate it. Static or kinetic friction times force normal is equal to the force of kinetic friction. So in this case, mu k times force normal. Let's see what a force normal is in this case. Well, luckily, this system is quite simple. Force normal is the only force that's opposing force of gravity 1. And this block isn't moving vertically. It isn't accelerating vertically. It's staying in one spot. So force normal is going to be equal to force of gravity 1. So force of gravity 1. So we can go ahead and manipulate this again. M2 times G minus Fg1 is going to be equal to the mass of 1 times the acceleration, which is gravity in this case. And if we can then put in our values, M2 is equal to 17 kilograms, M1 35, 17 kilograms times 9.8 meters per second squared minus 0, is that 28? Okay, 0.28 times M1, which is 35 kilograms, right? Yes, okay. Times 9.8 meters per second squared. And then we'll be able to calculate the net force, which is, in this case, let's go ahead and expand this. This is going to be equal to 106.6 newtons. No, my apologies. 166.6 newtons. And this right portion is going to be equal to oh, my apologies. Oh dear. It's going to be equal to 96.04 newtons. Which we could then simplify and calculate that the net force is going to be 70.56 newtons. Now, what is this net force on? Is this net force on just this block? Both blocks? If you chose the latter of those three options, then you are correct. It is on all two of these blocks. Because it's just FG2 minus FKF1 on both of these blocks, so the net force is going to be F net X in this direction. So let's see, what does that mean? So let's redraw this system again. This is essentially equal to M1 plus M2 FK1 FK1 and then FG2, which, as we already know, the net is going to be 70.56 newtons. This is the same as this system. I've just redrawn it so that we can we can visualize what is going on a little better. At least it helps me visualize what's going on a little better. And from here, it's quite straightforward. F is equal to mass times acceleration, right? So for this entire system, the F net is going to be equal to 70.56 newtons, which is equal to the mass total, which is going to be M1 plus M2 times some acceleration. And now we just solve for acceleration because we have M1 and M2, which is 17 and 35, some of which is, I believe, 52 kilograms, right? 35, 45, 50, 52, yeah. So we just divide 70.56 divided by 70.56 by 52 kilograms, and what we get is 1.3569 meters per second squared is equal to acceleration. The net acceleration of this entire system, and if everything is accelerating at this rate, this block and this block, that means this block is also accelerating at that rate, which means that this is also our answer. The block is accelerating at that acceleration. Okay, so now here comes the, I guess, trickier parts. Tension is a strange thing. And tension is, you can think of it as the force that is transmitted through the rope. But it would be, for example, if this is the rope, the tension force would be right here, probably pulling this way. It would be right here. So how do we solve for this? Well, how I like to solve for it is I take this out of context. Just only this. Only look at this. So let's redraw this over here. M2. FG2. Then we have tension, which is the force that is transmitted through the rope. Tension. And we're only looking at it at this context. So let's see what's going on here. Okay, so this block is supposed to be falling with a force of Fg2, which is equal to mass 2 times gravity, but this block is actually only falling with a force that is equal to m2 times the net acceleration, which is 1.3569 meters per second squared. And I'm running out of clipboard. Nice. Okay. 1.3569 meters per second squared times m2. It's only falling with this force. It's supposedly only supposed to be falling with m2 times 9.8 meters per second squared. This force is a lot less than this one. And in this context, we have to attribute it to something. And in this case, what we can attribute it, that decrease is going to be to force tension. So it's supposed to be falling with Fg2 minus tension, which is going to be equal to this, which we have here. So now we just solve for t. Let's manipulate this a little bit more. Fg2, subtract m2 times 1.3569 meters per second squared from both sides. And add t to both sides, and we'll end up with this final equation. Fg2 minus m2 times 1.3569 meters per second squared is equal to t. And if we just solve for this, m2 times 9.8 minus m2 times 1.3569, we already know what m2 is, so let me replace that. 17 kilograms is going to be equal to t. And this will bring us to our final value when we solve for t. It's going to be equal to 143.532 newtons. So hopefully you understood why I did the steps I took. If not, do pause the video, try to rationalize it, try to make everything make sense to you. And yeah, hope this video helped. I will see you guys next time. Adios.